So we haven't really talked about bases yet, but we'll talk more about these as we go along. Again, they're kind of the opposite of the acids. So soluble hydroxides, what are the soluble hydroxides? Hydroxides are all insoluble. Most of them are insoluble, except for which ones? Did you write down the rules from yesterday? Probably the best thing for the rules, for memorizing the rules, the solubility rules, is just to write them over and over again. Just write them. That way, if you're given a test, that's one of the first things you can do is, on the test, you could just write down the solubility rules and then just forget about them. But what do you have written for hydroxides? Yeah. And so there aren't that many soluble hydroxides because most are insoluble except for group 1. Group 1 would be sodium, potassium, lithium, cesium. All those hydroxides are considered strong bases. Group 1, ammonium hydroxide, strong base. And calcium hydroxide, strong base. Strontium hydroxide, strong base. Calcium, strontium, and barium hydroxide is strong base. All the other hydroxides are not considered strong bases. After you go through these solubility rules over and over again, so you have them down, you have them memorized, you have those down. And then, this is like I was listening to a documentary about Rome, and they were talking about the development of concrete and how that came about. And they're saying the development of concrete, one of the key factors was that people had time. They had time to think about these things, time to experiment. They had time because they weren't using all their time looking for food. I guess they had established farming techniques, and so they had more time to do other endeavors. Well, it's the same kind of thing. It's the same kind of thing with this. You might be pressed for time just to memorize the solubility rules. But then there are other people who have them memorized early on, and then, as they're reviewing them, they could look for additional patterns. And so at different levels, do you see any pattern? I know it's too early to ask you, but do you see any patterns in the solubility rules? Are those just straight memorization, or can you see something in there? For example, why are group 1 and ammonium salts all soluble? What are the least soluble species? What would you say the least soluble species are? What do the least soluble species have in common? Anything? Nothing? And so that's the type of stuff you do when you have the leisure of time. I know it's just a big effort just to memorize those, and it's tough because a lot of people can't memorize them. They don't have enough time to even do that. But the people who have the luxury of time, they've gone through, they've already memorized it, then they can start looking at other patterns. What is going on there. So one of the patterns is group 1 and ammonium are low charge. Low charge. The higher the charge, the less soluble. That has to do with the attractions, because what's holding the lattice together? Show you. Oops, that was a good lattice there. What's holding this lattice together? Yeah. One of the things that's holding this lattice together are things called ionic bonds. The ionic bonds are just the attraction between the positive and the negative. So if we have a positive ball, what does it want to do? It wants to surround itself with as many negative balls as possible. And likewise, if we have a negative ball, we want to put as many positives around it. The more positives we can surround a negative ball, and the more negatives we can surround a positive ball, the better, and the more stable it is going to be. And this is what we call ionic bonding. Ionic bonding forms this kind of lattice type structure like this, because we're just looking at positive balls and negative balls, and then just arranging the balls to maximize the interaction here. Well, what holds the balls together are electrical attraction between positive and negative. And so, does anybody remember Coulomb's law? Did I even talk about Coulomb's law? This kind of rings a bell. Somebody tell me, or remind me what Coulomb's law is. Not the electron one. It was way, way back. I think this was like in the first week of class or something, second week of class. It was way, way back. You know, hopefully something like Coulomb's law would be just easy now because it happened so long ago. Maybe I didn't talk about it. You haven't?
Unlike charges attract.
Yeah, unlike charges attract. And then it depends, you know, the strength or the force of attraction depends on two things. What are the two things it depends on? Did I talk about that or not? No, I didn't talk. Nobody has that?
What's the question?
The force of attraction depends on two things. The force of attraction is proportional to two things. The force of attraction is proportional to the charge on ball A times the charge on ball B divided by the distance between the centers of the ball squared, and so the size. And so basically we can summarize this as this, you know. It depends on the charge. Is the charge concentrated in a small volume? You know, if we have a high charge in a small volume versus the charge is dispersed over a huge volume. You know? And so let's say we have a +2 charge. If we have a +2 charge versus a +1 charge, which one's going to have bigger attraction or bigger repulsion? +1 or +2? The higher the charge, the more, like, what would you rather be shocked with? A higher charge or a lower charge? If you're going to be shocked. Well, you have a choice. You could be shocked by a higher charge or you could be shocked by a lower charge. What would you be shocked by? Well, neither. Actually, zero charge would be the best. But what would you pick? The lower charge. Why? Because it hurt less. Why? Because it's going to have weaker. And so the higher the charge, the stronger the force. The higher the charge, the stronger the force. Now, it depends on how concentrated that charge is. Is the charge concentrated into a tiny volume, or is the charge spread out over a huge volume? So +1 versus +2, which one's going to have a stronger force? +2, it's higher charge. Okay, now +2 over a big volume, or +2 concentrated in a tiny volume? Which one's going to have more force? +2 in a tiny volume. The more concentrated it is, the bigger the bite the charge has. And so that's basically what this is saying. This is saying the higher the charge, the stronger, and the more concentrated it is, that's related to the distance squared. The more concentrated it is, the bigger the bite. And so one of the patterns that in the solubility rules, typically if it's highly charged and small, then it's going to have a very strong lattice. If it has a very strong lattice, then it's going to be less soluble. Because when we dissolve a lattice like this, you know, in water, what should happen? Well, the lattice should break apart. Well, if the lattice is very strong, it's going to be harder and harder to break apart that lattice, right? And so what are the mostly insoluble species? What are the least soluble? The last,
The acids?
no, the least soluble in the solubility chart. At the very end of the solubility chart, what did we have at the very end? What ions? Or did you guys write down the solubility rules? Just look it up in your notes. What was the last entry? Phosphate. What's the charge on phosphate? 3 minus. High charge. High charge means strong force of attraction. You know, we've got a phosphate. It's going to be strongly attracted to the positive. Phosphates, what else? Carbonates are 2 minus and chromates are 2 minus. So high charge. High charge is group 1 ammonium, low charge. Also big. Those are big compared to some of the others. Silver ions are kind of small. Silver is one of the exceptions. When you look at it, it's not for group 1. When you're looking at the +1, silver chloride is very insoluble. Yeah, it's +1 like the group 1s, but it's different. The bonding's a little different from silver chloride. Well, those are the types of things that you could do if you have time, and you have time if you don't try to cram this in at the end. You know, if you cram it at the end, there's no way you can reflect or think back. The purpose of the repetition is there are 2 things. One, the purpose of the repetition is so you get it memorized down and you can recall it very quickly. And the purpose of the repetition is so that you can dig deeper into it, you know, and then you can think more deeply about these. In other words, you get to the next level, you know, beyond just people who just memorize it. They're just at the basic level. And this is like the Romans did with their concrete and architecture and that kind of scientific development. They had the time to do that, but most people don't, because most people are just cramming it the night before the test. So you could be different, for sure. You could be different if you wanted to, and if you have the time. And, you could have a big edge over most people. Big edge. So that's what I found at UCLA. Well, anyway, going on here, the soluble hydroxides, those are it, but those aren't the only strong bases. There are other strong bases too, so let's drop down the list here. The other strong bases are the soluble sulfides. Okay, what were the soluble sulfides? Group 1, ammonium, group 2. That's it. And so group 1, ammonium, group 2. Those are them. Now the sulfides do something different. The sulfides don't ionize. The sulfides do something else. They don't ionize, they hydrolyze. Hydrolyze is, hydro is water, lyze is breaking apart. They break apart water, the sulfides. So these are tricky. And so normally when we're thinking about these strong electrolytes, so the same thing with these bases. In fact, all bases hydrolyze. We'll talk more about that. Soluble oxides. Oxides, were those on your list? Oxides were not on your list. oxides were not on your list. But this is what makes a difference between next level versus base level. You know, base level person would say, okay, oxides were not on my list, therefore I don't need to know anything about them. Therefore, if I've ever asked a question on a test, it's unfair. You know, but you know, at UCLA, they don't care about fair or unfair or that type of stuff. That's long gone. Basically, they'll ask you something like this, but then you have to think, okay, do you know enough of the pattern to figure out what would you guess the oxides would be? You know, well, I guess the oxides are probably similar to maybe the sulfides, but we need a little bit more information. A little bit more information we're going to get later. A little bit more information would be that the oxides are a little smaller than sulfides, and so oxides are probably going to be less soluble. You know, like rust. Can you wash rust off cars with a hose? No. Iron 3 oxide, it doesn't wash off. And so the soluble oxides, let me just tell you, group 1 and ammonium. So we'll use a little bit of, we'll need a little bit of more knowledge in order to figure this one out. So this is still a little early for you guys to figure out. But there are going to be cases where, you know, things aren't on the list, and then you have to try to look at some patterns and infer what's going on. Soluble oxides. Okay, and then we have the amides. The amides are another anion that you didn't. The amides are NH2 minus. Etc. There are others, but these are the common ones here: the hydroxides, the sulfides, the oxides, and the amides. Amides are NH2 minus. There's another iodine that is just straight ionization; it doesn't come off the periodic table. I'll talk about what I mean by this. By this, don't ionize, they hydrolyze. All these hydrolyze. And a little bit later. Maybe I should talk about it. I'll talk about it a little bit later. Strong acids, on the other hand, they can do both, ionize and hydrolyze. So if we have a strong electrolyte, we expect to completely dissociate, ionize, or hydrolyze. So strong electrolytes completely dissociate, ionize, or hydrolyze water. Okay, let's look at the weak electrolytes next. The weak electrolytes consist of the heavy metals, some heavy metal salts, Okay, the heavy metals would be like lead, you know, mercury. Those are considered heavy metals. The metals down near the base of the periodic table, they're heavier. Those are the heavy metals. Periodic table here. Sometimes the bonding's a little weird here because normally when we think about metal plus non-metal, we form a ionic lattice. But sometimes when we have a metal and a non-metal, it forms a molecular compound. And so one example of that is lead. Lead-2 chloride is an ionic lattice, whereas lead-4 chloride consists of molecules. And if lead 4 chloride is soluble in water, when that lead 4 chloride molecule dissolves in water, some of it can break a little bit. Potentially dissociate. But we're not going to get into specifics here. We'll just look at these weak acids. All right, weak acids are, they're going to begin with an H, and then they're going to have some anion. H anion, whatever the anion is. The anion is going to vary. So if acid is not strong, then assume it's weak. You're pretty safe there for most of the time. How many common strong acids are there? 7. If you memorize those 7, then you can assume all the others are weak. Then you'll be right most of the time. There are going to be some uncommon acids that are quite strong, but hopefully you don't encounter those, so you're okay here. So if the acid is not strong, then assume it's weak. And then we have the weak bases. The weak bases do the same thing. The weak bases don't ionize, they hydrolyze. And the weak bases, we look at this up on a chart. Pretty soon we could figure it out once we know some more about structure and that kind of stuff. Look up on a chart. And then we have the non-electrolytes. The non-electrolytes are everything else. If it's not strong and it's not weak, then it's going to be a non. And so these are the rules for electrolytes. The rules aren't perfect, but will give us a pretty good idea. So we're going to take a look at different compounds and categorize them. All right, so sodium chloride, is that a strong electrolyte, weak electrolyte, or non-electrolyte? So sodium chloride, is it soluble or insoluble? First we look at the cation. When you look at that cation, it's a group 1, sodium. And so this is a soluble salt. Therefore, soluble salts are strong electrolytes or weak electrolytes, or non-electrolytes. They're strong. And so when it dissolves in water, it should break up or ionize or dissociate into ions. So that's what we see here. Copper 2 chloride, which is normally solid. Both of these are normally solids. Copper 2 chloride, is it soluble? So first we look at the cation, group 1 ammonium. Well, it's not one of those. Then we look at the anion. Nitrates, acetates, chlorates? No. Chloride. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. Lead 2 and mercury 1. So this is soluble. And so what happens is when we dissolve it in water, it breaks up into, or completely ionizes, breaks up into the ion. This is what happens to, this is sodium chloride here. And so if we have salt crystal here, what happens is the lattice gets broken apart by the water molecules. And as it dissociates, the ions are now mobile. these ions are going to be surrounded by water molecules. If you take a look at the pattern here. You see the hydrogen ends are pointed here towards the negative ion. The oxygen ends here are pointed towards the positive ion. And that's because water is what we call polar. Water has a positive end and a negative end. The hydrogens are positive, and therefore we're trying to maximize the favorable interactions. This is Coulomb's law. And so the water, the hydrogen ends are pointed towards the negative here, and the oxygens on water are negative, and therefore they're going to be pointed towards the positive. And so this helps stabilize the ions. These are called hydration spheres, see, or solvation spheres. It helps stabilize it. And that's how we can break apart that lattice. We can break apart that lattice here, a +1, -1, but let's say if this were +2, -1, or +2, -2, it's going to be a lot harder to break apart that lattice. Right? If this is a +3, it's going to be much harder to break apart that lattice. Well, this is +2, -1. I guess this lattice breaks apart. Well, water's not. So we see the lattice here. And the water molecules are just going to, we dissolve that. It's not infinitely soluble. You know, some things are infinitely soluble. That is, you can dissolve as much as you want in there. You know, there's a limit to how much you can dissolve in there. And where can we find out that limit? Like the number of grams we can dissolve in 100 milliliters. Where can I find out that type of information? Wikipedia. Yeah, do that. And so what we have here, we have the hydrated, take a look, that's a +2 that's surrounded by the oxygens of water. This is a minus that's surrounded by the hydrogens in water. So that's the copper 2 sulfate. And so, copper 2 chloride. When I have copper 2 chloride, it all right, so now what is this called here? Potassium sulfate. Good. Is potassium sulfate soluble? First you look at the cation. What cation is it? Potassium is group 1. All group 1 salts are soluble. And so potassium sulfate is going to be soluble. And so we should write the equation. The equation for dissolving this is, does it split apart? Does it ionize when we dissolve in water? Yeah. I do it in 2 steps. Your book does it in 1 step because I look at these two differently. The first step is solubility. Is it soluble? Yes. And so what I'm going to form is I'm going to form potassium sulfate aqueous. Potassium sulfate aqueous. And then I ask, okay, it dissolves in water. What happens after it dissolves? Does it dissociate completely, partially, or not at all? And this one dissociates completely. And so the next step is electrolyte. Okay, what does it dissociate into? If I break this apart, it's going to dissociate into potassium ions and sulfate ions. But I have to make sure it's balanced. How many potassium ions am I going to form for every K2SO4? For every K2SO4, I'm going to form 2 potassium ions and 1 sulfate ion. That's to keep things balanced. So 2 potassiums and 1 sulfate. Okay, these are going to be aqueous species, dissolved in water. And so I do it in 2 steps. I first look at the solubility, and then I look at the electrolyte. So just because something's soluble doesn't mean it's a strong electrolyte. And so they do it in 1 step. 2 potassiums, 1 sulfate. Write the ions present in the solution of calcium. What's that? Calcium how do you name that? Calcium nitrate? Yeah, calcium nitrate is correct. Yeah. Is calcium nitrate soluble or insoluble? First we look at the cation, group 1 in ammonium. No, it's not group 1 ammonium. Then we look at the anions. Chlorides, well actually nitrates, chlorides, acetates, no. Chlorides, bromides, iodides, no. Oh wait, no, I missed it. Nitrates, chlorates, and acetates are all soluble, so it's soluble. And so what I do is this. Calcium nitrate, most salts, in fact, practically all salts are solids. There are some rare ones that are liquids at room temperature, but most salts are solids. Calcium nitrate, is it soluble? Yes. And so first I look at solubility. It is soluble, so it's going to dissolve in water. So what we're going to have is we're going to have calcium nitrate, AQ. Then I ask this. Does it ionize completely, partially, or not at all? What would you say? It ionizes completely into what ions? We're going to tear apart the lattice. We're going to get calcium ions and nitrate ions. Like this. We're going to get 2 nitrates that break off for every calcium nitrate. And so this is the way we visualize this solution. If I have a beaker of this solution, I'm going to see a CCS. Those calcium ions, nitrate ions are colorless. So this is going to appear as a C. What does CCS stand for again? Clear colorless solution. Again, so this beaker is going to be labeled calcium nitrate AQ. The beaker is going to be labeled like that. But what am I going to find inside this solution? I'm going to find calcium ions, a bunch of them, calcium ions and nitrate ions. Nitrates are going to be a little bit bigger. They're going to have a shape to them. I should probably do it. This. These ones are going to be stabilized by having water molecules surround themselves. For example, water molecules will surround themselves around calcium 2+. The oxygen end of the water molecules or the hydrogen end of the water molecules will surround themselves with the calcium 2+. The oxygen end. So the oxygen ends are pointed towards these. And then for the nitrates, it's the hydrogen ends that are pointed towards those to help stabilize them coulomically. And so that's what we get here. And so a solution of calcium nitrate does not contain molecules, does not contain lattice, it just contains ions, individual ions. They're floating around there. And so it's a strong electrolyte. So this will conduct electricity quite well because those ions are free to travel, to translate, resulting in electrical conduction. What else are strong acids are strong electrolytes. Strong acids, weak acids are weak electrolytes. So let's take a look at an acid here. Okay, an acid is a substance that has a proton that can be removed by water molecule in solution. All right, let me rephrase that. This is a Bronsted acid. A Bronsted acid has an H hydrogen. X is a generic anion. So they're just using X for some negatively charged anion. Okay, this first reaction here is this. Water is a very interesting species because water is both an acid and a base. You know, it can go either way. Depends on what you mix it with. And so this first reaction here is We have ionization and we have hydrolysis. And so let's take an acid. Example, HCl. HCl, is it a strong acid or weak acid? It's a strong acid. Well, HCl is normally a gas. Is HCl soluble in water? Yes, HCl is soluble in water because HCl and water are similar. How are they similar? They're similar in something called polarity. Because there's a negative end of water, which is the oxygen, and a positive end of water, which is the hydrogen end. Well, HCl has the same kind of thing. There's a negative end of HCl, which is the chlorine, and the positive end, which is the hydrogen. And so we call that polarity. And so both water and HCl are both polar, whereas oils aren't like this. Oils don't really have a positive and negative end. So oils are called non-polar. We're going to look at this in much more detail when we get to structure. But for right now, let's leave it there. And so HCl is soluble, so we're going to form HClAQ. Now if I have HClAQ, what's present in solution? And so there are two ways I can deal with this. HClAQ, I can ionize this or dissociate. Ionize, dissociate, kind of same kind of deal when we're talking about electrolytes. Or I can hydrolyze it. Okay, if I ionize it, it just means it splits apart into the ions. So it's split up into the H plus ion and the Cl minus ion. H plus and Cl minus. It's a strong electrolyte, so we expect it to ionize completely or dissociate completely. If I hydrolyze this, all it means is I'm going to combine it with water. When I combine it with water, what happens here is this. Acids, they lose the H plus. And so acids lose an H plus, that means the water gains it. So I'm going to get H3O plus. Now this water is going to have 3 hydrogens. This is called hydronium. This is another ion that you have to memorize, the hydronium. But the hydronium is formed when you take acid and put it in water. Then we'll get hydronium. You don't, like, for example, you don't go and say, okay, I want to buy some hydronium chloride unnecessarily. Usually, it's not something that they isolate. It's something that forms. And then we're going to get the chloride here. It's chloride moved over. And so this is called hydrolysis. So HCl aqueous plus H2O liquid gives hydronium aqueous plus chloride aqueous. Both of these are kind of the same thing, basically. What they're showing here is hydrolysis. So, strong electrolytes ionize or hydrolyze completely. And so here, this is HCl. HCl is strong acid. It hydrolyzes completely. And so what we're going to be left with is just hydronium and chloride. So we might have started with HCl, but we're going to be left with hydronium and chloride. How about this? What's this acid? What's the name of this one? Nitric acid. Nitric acid is a strong acid, or? Strong. Yeah, strong acid, so it's going to hydrolyze completely. And so this is what we'll see. When a beaker is labeled, let's do the beaker of nitric acid. When we have a beaker of nitric acid, what are we going to find inside that beaker? Well, one thing is it's going to look like a CCS. CCS. Sometimes there's fumes that come off this. Sometimes there's fumes, brown fumes, that can come off this. That comes from a reaction. Brown fumes that come off this are from a reaction that produces when it reacts with something. But in general, if we have a beaker of HNO3 like this, it's going to be labeled HNO3AQ, but what is HNO3? What's inside that beaker? What's inside this beaker going to be, we're going to have hydronium ions and nitrate ions. That's what's inside this beaker. Hydronium ions and nitrate ions. And those are just going to be floating around in there. The same thing with a beaker labeled HCl. What are we going to expect to find? We're going to expect to find hydronium ions and chlorine ions. Are we going to expect to find any HCl molecules? No, there should be no HCl molecules present, and there's going to be no HNO3 molecules present either here, because all the molecules will have been broken apart. All of them. This is a strong electrolyte. H2SO4 is what we call a diprotic acid. Hydrogen ions sometimes are called protons. Not just sometimes, but oftentimes they're called protons. And so it's a diprotic acid because there are two. If you look at the two. Do you recognize this acid here? Okay, how about the anion, 232? Do you recognize that ion there? Acetate. So this would be acetic acid. This is a monoprotic. This is diprotic. Diprotic has 2 hydrogens. Monoprotic has 1 hydrogen. But you go, what about these 3 hydrogens over here? These 3 hydrogens over here are different structurally than this. And so we have 1 hydrogen that's acidic. The other 3 are what we call non-acidic hydrogens. Phosphoric acid would be an example of a triprotic acid. And so if we look at H2SO4, this is what's going to happen with H2SO4. The hydrogens break off one at a time, or dissociate or ionize one at a time. And so H2SO4 is a 2-step process because it is a diprotic acid. Now, H2SO4, it's soluble. Acids in general are soluble. So H2SO4 is aqueous. So we'll skip the soluble step and then go straight to this. Now, H2SO4 is a strong acid, so it's going to hydrolyze or ionize completely. So if I ionize this, I'm going to ionize it into H plus and HSO4 minus. Or if I hydrolyze it, I'll do H2SO4 plus H2O liquid. This is going to produce H3O plus HSO4 minus.
So if we do an ionize or hydrolyze, they will both be correct?
They would both be correct. My preference is to do the ionize because it's easier. But there's a situation here is this. The situation is H plus. Well, what does a hydrogen atom consist of? H atom. Let's do the H1. What does a H1 atom consist of? How many protons does H1 have? 1 proton. So it's got 1 proton in the center, so that's 1 positive charge. How many neutrons? H1 has 0 neutrons. 1 proton and how many electrons? 1 electron. That's the atom. Okay, now if I do the H1 plus cation, what do I have? What does the H1 plus cation? Now, the H1 plus, it's got a positive charge because it must have lost an electron. If it lost an electron, then what's left over? What's left over? So what is the composition of the H1 plus cation? It's a proton. And so H1 plus just consists of a proton. So this is why H plus is often called a proton, because that's all it is. It's a proton. Unless you're dealing with H2. H2 would be deuterium. It has one neutron and a proton. The charge on a proton is only +1, which is no big deal. What the big deal is, it's the size. You know, if we look at a +1 ammonium ion, ammonium is NH4, kind of big. NH4, and it's got a +1 charge. If you look at sodium ion is kind of big too. Sodium ion, big, +1 charge. But how big is a proton? How big is a proton compared to an atom? About how many times smaller is a proton compared to an atom? If an atom were the size of a football field, how big would the the nucleus be? Did anybody write it down? Nobody wrote it down? I said the nucleus is this many times smaller than the atom. Anybody write that down in their notes? 10,000 times smaller. Good. You just want to be able to recall it quicker for time tests. It'll give you a huge edge as well. But it's about 10,000 times smaller. And so if we look at a sodium is like this, huge. Or even a lithium is huge. And so Li plus is huge. It's going to go like this. Remember group 1. Group 1, what's the charge on group 1? What does group 1 consist of? Group 1 consists of hydrogen, lithium, sodium, potassium. And so if we look at lithium ion, the Li plus is huge compared to the H plus. The H plus is like a tiny, tiny dot. It's a tiny, tiny dot. You can't even see it, but the Li plus is huge. And so what did I say about this? As far as Coulomb's law. In other words, for Coulomb's law, we like to think in terms of something called charge density. Charge density is how concentrated the charge is. The higher the charge density, the more concentrated the charge is. And so if you have a positive charge in a huge volume versus a positive charge in a tiny volume, and this tiny volume is going to be more than 10,000 times smaller. Let's just keep it at 10,000 times smaller. So you put a +1 in a volume that's 10,000 times bigger. Okay, this is like, okay, I have a bottle of chlorinating solution. I pour the bottle of chlorinating solution in a kiddie pool versus a huge pool, which is 10,000 times bigger. You know, that's charge density. And so what's going to happen is the charge is going to be diluted heavily in the bigger versus the smaller. And so which one should be more reactive? A proton or a lithium ion? Based on charge density. Lithium ion should be more, you get more of a shock from a lithium ion than a hydrogen ion. Maybe it's not. Okay, how about sodium versus potassium? Which one is more concentrated, the charge? In the sodium or the potassium? In the sodium. Because the positive, they're the same charge. Same charge. Shouldn't they both be equally reactive because they got the same charge? True or false? False. Sodium is going to be more reactive because the charge is more concentrated. The more concentrated the charge, the more reactive it's going to be. The more concentrated the charge, the more reactive. Okay, how about this sodium? Lithium is smaller, so which one's more reactive? Lithium or sodium? Lithium. And then how big is a proton? It's like going to be at least 10,000 times smaller than that. This is going to be a tiny, tiny dot. That's the hydrogen ion. Which one's going to be more reactive, the hydrogen ion or the lithium? The hydrogen, by orders of magnitude, the hydrogen ion is going to be much more reactive. Hydrogen ion is very unusual because it's only the nucleus. This is the full atom because there's still electrons. Lithium just lost one of its 3 electrons. Sodium lost one of its 11 electrons. You know, these still have a lot of electrons. This atom's still big. Still a lot of empty space there. This thing, there's nothing there. All that's left is a tiny, tiny nucleus. And so this is what this means here. Note, both are acceptable. But only one is correct. Which one is correct? Or more correct? The right equation or the left equation? Right. The right equation. Both are acceptable because H plus AQ is too reactive to exist in water. Therefore, H plus AQ is hydronium. You know, it's not balanced, but we take it as hydronium. H plus AQ is hydronium. So this is not balanced. It's not equal, it's just taken as hydronium. And so this is a shorthand way of doing things. You know, to have to write hydronium out all the time becomes a bit of a hassle. And so it's just much cleaner, much easier not to have to add this water and then convert it. Because what happens is H plus is so reactive that immediately when it comes into contact with water, H plus immediately when it comes into contact with water, it reacts to produce hydronium. This is a very favorable reaction here. And so H plus will react immediately with water. To produce hydronium. And so H plus doesn't exist here. It's too reactive. So if we ever see H plus AQ, they must be talking about hydronium. So we have to do an extra step. The H plus AQ, any of that that's generated is so reactive, it reacts right away with water. Let's do some examples of coulombs. Here's one example of coulombs here. EDTA is an organic anion. It's big. The formula is a bit complicated, so a lot of people abbreviate it just EDTA. It's a 4- anion. It's 4-, it's not just concentrated on one. There's -1 charge on multiple atoms, on 4 atoms in particular. EDTA has this formula. EDTA's formula is well, it kind of has this structure here. So since the formula is so big, they oftentimes will just abbreviate it EDTA 4 minus. This is an anion. So if we have sodium EDTA versus calcium EDTA, which one do you think is more soluble? Which one do you think is more soluble? In other words, which one do you think dissociates easier? Which one do you think dissociates more difficult? Sodium EDTA should dissociate easier than calcium EDTA. If it dissociates, then what it does is it frees the EDTA to do its job. EDTA has a job. And one of the jobs of EDTA is what we call a chelating agent. So EDTA loves to scavenge for metal cations and capture those. And so EDTA is used for things like lead poisoning. Lead poisoning, we'll use it. So which one do you think would be better or more aggressive for lead poisoning? The sodium EDTA or the calcium EDTA? What we want to do is we want to free up the EDTA to let it do its job. Which one would you think would? The sodium EDTA. So actually, both of these drugs were once available. These are two drugs that are used for lead poisoning. Which one do you think is more aggressive treatment for lead poisoning? Sodium EDTA or calcium EDTA? EDTA is the active ingredient. Sodium, or you say calcium?
You said aggressive. You said aggressive.
More aggressive. Which one would be more aggressive, sodium or calcium? Sodium? Why do you think sodium will be more aggressive? It's faster acting, yeah. It's faster acting because it's not hindered by, this calcium. Calcium is what's the charge on calcium? Calcium is a +2 versus sodium. So EDTA can break free easier from sodium than it can from calcium. Does that make sense? So EDTA can, therefore, which one of these two would you think is more aggressive? Sodium EDTA or calcium? I'd say sodium, because the EDTA can break free easier from sodium ions than from calcium ions. The calciums are going to hinder it. Make it less aggressive. The EDTA, if the calcium ions are hanging on to the EDTA, it's going to be less aggressive than calcium. Why would calcium ions hang on to EDTA more aggressively than sodium ions? Higher charge. And so this is called chelation therapy. It talks about chelating agents. There are two. There's something called calcium EDTA, which they abbreviate to CA-EDTA, and sodium EDTA, which they abbreviate Na2-EDTA. But there's actually, there's got to be another cation there. The other cation of two sodiums that they don't show. But anyway, this is chelating agents, especially those intended for use in children, should be effective in reducing lead and other heavy metals from the body without producing substantial adverse effects on levels of critical serum electrolytes such as calcium. The only agent recommended for intravenous IV chelation therapy for children is calcium EDTA. However, hospital formularies usually stock multiple chelating agents. One such agent, sodium EDTA, was formerly used for treatment of hypercalcemia, but its use has become infrequent. Furthermore, sodium EDTA contains a warning stating that the use of this drug in any particular patient is recommended only when the severity of the clinical condition justifies the aggressive measures associated with this type of therapy. According to the package insert, sodium EDTA is indicated in selected patients for the emergency treatment of hyper. Hyper is, too much calcium, and for the control of ventricular whatever. According to FDA and CDC, the safety and effectiveness of sodium EDTA in pediatric patients has not been established, and its use is not recommended because it induces hypocalcemia. So this is like, okay, let's say you're working in a hospital. There's a bottle of sodium EDTA, a bottle of calcium EDTA. How do you treat those? Would you say, oh, they're the same thing? EDTA is the active ingredient, EDTA is EDTA. Whether it's sodium or calcium, doesn't matter. I can just use either bottle. Is that what you'd think? No. So look at this case report. February 2005. A girl aged 2 years who was tested for blood level during routine health surveillance had a capillary BLL blood lead level of 47 micrograms per deciliter. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood lead levels. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. The patient's blood electrolytes admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Sexamer, an agent primarily used for treatment of lead poisoning. The medication order subsequently was corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35 p.m., she was administered 200 milligrams of oral Sexamer. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter. Normal value for pediatric patients, 8.5 to 10.5 milligrams per deciliter. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and a cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level is less than 5 milligrams per deciliter, despite repeated doses of calcium chloride. All attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. Yeah, so sodium EDTA, calcium EDTA, no big deal, same thing, right? No, that's quite a bit different as far as that goes. I mean, this goes on. Pennsylvania, 2005, 5-year-old boy died. 2003, 53-year-old woman. All from giving sodium EDTA instead of calcium EDTA. And so this is CDC report. There are other deaths. The CDC recommend this. You know what they recommended after the conclusion of this study? They recommended get rid of sodium EDTA, so it's no longer on the shelf, so people cannot use it. So they don't have sodium EDTA anymore. I think it's only calcium EDTA because of this error. Well, anyway, this is just from 2003 to 2005. Okay, so we'll stop here. We'll take a break, and then we'll start again after the break.